Yes, good evening to our audience. And on this occasion of Engineers Day, I would like to welcome you all to this 35th webinar, which we are having on the e-discovery series from Tata Tiscon. It gives me great pleasure today to introduce our speaker, Mr. Amandeep. So Mr. Amandeep, of course, is a very renowned professional consultant, and he has served at the Bureau of Indian Standards, HSCC India, and R&D for Innovative Technologies at NMCEZ. He is also an expert member at various BIS technical committees. Welcome, sir, and thank you so much for being our speaker today. We will introduce the topic, which is high strength steel reinforcement and detailing. And we look forward to having a very informative and interactive session with you, sir. Over to you.
Thank you. Well, first of all, I would like to give my best wishes to all the engineers on the occasion of this Engineers Day, and would like to thank Tata Tiscon to give me the opportunity to share my views on detailing, especially for the high strength reinforcement steel today with all of you. To start with, I would just like to brief you that my presentation would contain more more details about the detailing for the dynamic load safety, like why we should go for ductile detailing, what are the practical constraints at site, how we can achieve that. And I would like to welcome all your questions even during my presentation. But I would take up the questions at the end of the presentation, and you are welcome to write your questions whenever the question come to your mind. So I would like it to be a very informative and interactive session today. We all know that the reinforcement steel plays a very important role in any of the RCC structure. So it would be beneficial for all of us to understand the concept of high strength and the concept of detailing, and not only detailing in the drawing, but also how to make it executable at site and really executing it to achieve the benefits what we are intending. So I think it is now a right time to start the presentation. So I will take up the presentation with my slides. So my first screen is visible to all of you. I hope the screen is visible.
Yes, sir, it's visible.
So should I close this screen? Okay. So now I take up the presentation. So all the attendees are muted, so you can only ask your question through the chat box or the question box, which we will be taking. During the presentation, I would be having two surveys, and you would be able to give your opinion during those surveys. So first of all, we should understand that the construction which is being taken place in the country are of two types. One is non-engineered construction and the other one is engineered construction. When we talk about non-engineered construction, it means any construction which is being done spontaneously without proper planning, without involvement of technical inputs of structural engineers or other civil engineers, and it is to the wisdom and the experience of the artisans or the masons, and without structural load calculations, just based on past experience, constructions are being done, and that we call as non-engineered construction, because there is no computation of the forces, stresses, and is being done without any technical support. Generally, up to 2-3 story buildings are being done in our country without technical support, which are generally residential. And I would say that more than 50% of the construction of the country in today's time also is being done without technical support. So at one place we are saying that engineers are available without employment, but at the other side engineers are available, but the engineering inputs are not going into the construction industry. So that is where we all should need to work on, to give technical support to the areas where we need it most, like for the residential construction in even 2 or 3 story buildings also. Engineer construction, we classify it as a proper design building, whether it is masonry building, timber building, steel building, prefab structure, where all the stresses and forces are being computed by the engineers to work out a safe design and execution as per the codal provisions of the country, and to make the structures safe and durable. So what should be the aim of the engineered construction? So when we target to have engineered construction, we always aim that the building or the other structure should perform satisfactory during the intended service life. Now, what is the intended service life? A life which an engineer wants that the building or the other structure should satisfy or to survive with the functions intended to be used. Like if we consider a building, if the engineer says that I want the building design to live 100-year life, then what all has to be considered? If we want a temporary construction, say we say that it is a temporary work, after 15 years we may not require this, so it will be considered as a temporary construction. If it is a lifeline construction, say it is a metro station building or some dam or some very special construction where we need a very higher life, maybe infrastructure like metro track infrastructure, railway stations, or maybe police station, or maybe hospitals, where we may require a higher service life of the building, maybe 120 years, maybe 125 years, then again we have to think about that. Generally, in our engineering colleges, we intend to design based on the strength criteria. And we generally calculate the bending moment and we design it to complement with the bending moment of resistance. So we first calculate the demand and then we provide the concrete and with reinforcement to meet that demand. But at the same time, we should be always thinking that what would be the intended life and how we will achieve the service life of the structure. The other objective is that it should be able to sustain the loads and deformations of the construction and use, because at the time of construction also there may be some higher stresses, and we should be able to design the structure that during the normal use it should be good enough. During construction phase also the building should not get any distresses, and general use it should live the whole life as we intend as a service life. Adequate durability is also one of the main objective. The durability, when we say durability, it means there should not be much requirements for the say repairs. We do not say that there should not be any maintenance cost. Of course, any structure, any building would require proper maintenance. Just like we as a human being, if we get some kind of say fever, we need to take some kind of paracetamol or some medicine. So general maintenance or general kind of repairs is fine, but if the structure is getting damaged very sharply to a very high extent, it means there have been some engineering issues and our aim is not getting fulfilled. So to fulfill that requirement of durability, that the building should not go to repair again and again with a higher cost, we should have a proper system of engineering design. Another objective is to have resistance to effects of misuse and fire. And when I use the term misuse, it is not the intentional misuse, but sometimes suppose a structure is designed to have a load of say 400 kgs per square meter, but due to usage time, sometimes it can go to 450, or maybe during construction some 5-10% plus minus loads are there, or maybe a small fire is there. Due to fire effect there is some kind of distress that should be taken care by the building by itself. So if we have to meet the requirements of the aims of the structural designs or structural execution. What is all required? The required is to be getting competent engineer. Now today we have the Engineers Day, so I feel all the audience which are attending this course have an attitude to learn. They want to become a competent engineer. That is why you are sparing time to attend this program. So attitude is first, and then you have to develop the skills. Probably this session of 1 hour would add something to your skill, because I would be taking care to add some things which are generally not available in textbooks. And then of course, whatever we are discussing today would add knowledge to everybody. So when we call as that we have to be competent enough, it would need attitude, skill and knowledge. So I appreciate all of you who are attending this seminar, this program, that they have at least the attitude to become a competent engineer. And and my best wishes to all of you, that you become best of the class of the engineer to serve the country, to get best of the constructions. So now taking you to the approach to the engineer development. This is a basic requirement for any construction project, that first the selection of site should be proper. The uh, the the land which we are going to develop should be developable. I am seeing some projects which are being developed in marshy land, very difficult scenario, the locations where there are a lot of landslides or floods, and these are the areas which we should generally avoid. If it is unavoidable, then after proper engineering studies only we should use those sites. Of course, the cost of using those locations would be very, very high. But if it is unavoidable, then we should not just do it like for a suitable area. If this location is not a good site, then of course all geotechnical investigations and other areas like for landslides prevention, some retaining wall systems, for flood prevention system, all the measures would have to be required to be taken care. Now our focus is today is mainly on the design and detailing. In today's session, I am not going to talk much about the design calculation part, but my focus would be on the detailing of the reinforcement. Selection of material, of course, because we are now going to discuss about the reinforcement. When we talk about reinforcement, what comes to our mind? In our mind, what generally we discuss is about mild steel or HYST bar, high yield strength deformed steel bars, or nowadays what we call as this TMT, thermomechanically treated high strength deformed bars. So this is not the only material in the world to be used as reinforcement. Reinforcement may be of other type also. Some people are using bamboos also, or maybe some basalt rods, maybe some fiber rods, maybe carbon rods, E-glass fiber FRP rods. So there may be other options also in time to come to be having a usage like a reinforcement. But for normal construction, what we find is the optimum arrangement, the combination to get a composite structural RCC behavior is generally with the reinforcement steel. So we are going to talk about the steel detailing only. Though some people may say that why only steel, why not other things? Other materials are being used for very, very special applications, and they might be the costlier options also, or may not be suitable for any normal kind of construction. So, but just to give you a clue that reinforcement steel is not the only option, but option which is to be the best considered option for normal constructions. It is generally considered as the most economical also. Now, systems of construction are also important. Sometimes we go for precast construction, pre-stressed construction, normal RCC in situ construction, or maybe some composite type of construction wherein we can use some structural steel systems along with RCC systems. So all these systems also play a very important role when we talk about the engineered construction. Of course, very important part for the durability and serviceability of the any civil development is the drainage. Whether it is rainwater drainage or other water which is coming near to the construction should be drained out. Now, water is the biggest enemy of the reinforcement steel. We all know. Water, if is available along with air in the reinforcement, it triggers the corrosion or deterioration of the RCC elements. So corrosion of steel, if we have to prevent, we should have a proper system of drainage, and we have to have a system where we can prevent water to come inside the RCC elements to give any kind of damage to the RCC steel. Then we have MEP services important for the projects: mechanical, electrical, plumbing, sewerage, drainage. All these services play a very important role for a successful project. And last but not the least, I would say that the waterproofing for a project plays a very important role in preventing the damages due to corrosion of the reinforcement steel. So we should do proper waterproofing in all the open areas, like for balconies, for the areas which are exposed, like for shaft areas for the toilets and terraces, or sometimes if you have basement, then basement retaining walls, basement foundations. So all these things where all these structural elements which can be get damaged due to water ingress should be taken care by adequate waterproofing. And of course, after the construction, the regular inspection and maintenance brings the actual service life which we intend to give as an engineered construction. So taking you to the level where we say that in our country we need to have a proper detailing of the reinforcement steel, because we all know that concrete is good enough in the compression. So if we have only axial force, compression force, then probably we need very nominal reinforcement just to prevent some shrinkage cracks or some thermal expansion. But seeing this diagram, if you are able to understand that our country, where we have a lot of thrust faults, fault lines, structural trends, which can trigger small to mild to a high level of earthquakes. So earthquake can trigger a very big damage to these structures. Nowadays you usually see in any part of the world, and every month there is a damage due to earthquake, and we don't want that. When the building has been designed with proper engineering inputs, should have any damage due to any earthquake. So our country has been divided in earthquake zones, and all the analysis and design is done for meeting the force requirements, force or the strength requirements of the earthquake zone. So we are today discussing about the detailing part, and in the detailing, we understand that maybe all of you would be knowing that India is having earthquake zone 2, zone 3, zone 4, and zone 5. At this moment, as per the IS 1893-2016, we have these 4 zones, zone 2 to zone 5. But the revision of the standard is in progress, and very soon we would be having zone 6 also. So criticality of the earthquake is increasing as we increase in the zone, and almost 50 to 70% area of the country is in a higher earthquake zone, I would say, a zone where we have susceptibility of the damages due to earthquakes. So this diagram is just only to show you that almost everywhere there are the risks of the earthquakes. Somewhere it may be mild, somewhere it may be. So I would request for my first poll question here, that how our engineers are considering the reinforcement right? So you would be having a, a poll question. So poll, I think poll has been displayed.
Yes, sir. The poll is displayed, and we would request all participants to please give their vote in this particular poll down.
So should I continue, or I should wait for a minute to the audience to participate in the polling?
Yes, sir. Maybe we can wait for a minute.
Okay, thank you. Okay, so all results have been displayed. Can I also see the poll results?
Yes, sir. It's on your screen. I think the result is being displayed. So, as per the results which have come in, which parameter of steel reinforcement is beneficial in the case of tall buildings? 14% have voted for higher strength, 17% for ductility, and 69% have said both.
Yes, very good. So, so all of you have a very good understanding about the requirement of the reinforcement steel, because I have taken specifically for the tall buildings, because tall buildings have a very great impact on the reinforcement type or reinforcement parameter. Now, as most of you have already thought, have clarity of thought that not only the strength but also the ductility is very important for any tall building. Generally, in earthquake zone, so it is the ductility requirement is the essential requirement. So we use super ductile or ductile grade of steels in the super tall buildings in higher earthquake zones, but in lower earthquake zone also, because there is no zone 1. So we cannot say that any part of the country is having zero earthquake risk. So there is some mild risk of earthquake in any part of the country. So it is always advantageous to use ductile steel. And now my screen, if you are able to see, is showing what is the ductility, what is the ductile design. Now you see this graph in which you have in the vertical side the force, and in the horizontal direction we are seeing the displacement D. So you see in the first blue line, it is the conventional strength based design. In the strength based design, what happens that you have higher force capacity, or you say that you have very strong system, just like if we see very old structures having 2 meter thick walls or column sizes of say maybe 2 meter by 2 meter, something like that. So the strength part is being considered. If we see Rashtrapati Bhavan or many other type of structures conventionally made, these buildings were based on higher strength parameter. So you see, because the structural elements are very big, maybe the reinforcement provided is very large, so they are able to sustain high level of force. But if the earthquake is large and the deformations are more, then it will not sustain. So it is allowing very low deformability. After a certain force capacity level, it will not withstand any further rotation or displacement. But if you see in this screen, this red line, which is showing a ductile behavior of the structure. And if we want to like to define the ductility, what is ductility? Ductility is basically deformability without failure. So you see this red line shows very high level of deformability. Deflection is going very large, and it is not failing. There are some minor cracks you can see in the junction. These horizontal vertical lines are there, which can be shown as cracks in the structural system. But structure system allows a large deformation without any collapse or failure. And these cracks basically are the plastic hinges. So if we have to allow these cracks to happen and the structure to deform so large, then our detailing need to be very special. We all know that concrete is a brittle material, and as the system will deform, the concrete will tend to crush or crack. So to give adequate capacity of shear at the junctions, we have to be very sure about the reinforcement detailing. So today we are targeting that all of the attendees should be able to assess, understand the requirements of this ductility at the junctions, so that we understand and ensure that these hinges are made wherever these have to be made in case of severe earthquake, but our structure is not going to damage. Because in today's time, we cannot afford to have strength-based design, because strength-based design will be costing too much and it will take a lot of space. The column sizes will be too large. The beam thicknesses will be too large. The overall costing will may go up to 30-40% higher than the ductile system. So if we can have very economical design wherein we can cover the risks of any deformation due to earthquake, then definitely we should go for ductile system. And our Indian standards mandate that for all the main buildings of zone 3, zone 4, zone 5 have to be detailed with ductility system. Only zone 2 buildings are given option that whether if they like they can go with strength based system, and they are also open to go for ductile system. So in my opinion, as far as economy is to be considered, in zone 2 also sometimes ductile detailing becomes economical in the overall costing. So we let us go and understand how we can detail it. Before further moving to the actual detailing, I just want to make you understand that with the system of ductile detailing, what we are achieving is that due to cyclic rotational or deformation during earthquake, our behavior of the joints become so uniform and it is dissipating so much of energy that the structure can easily withstand with a lot of earthquake energies which are transferred to the building without any damage. You see the other graph, which it shows the structural steel elements to be performing under the cyclic loading. So these hysteresis loops can help you understand how a structure would perform during an earthquake, right? So this is again notation that when we have strength-based design, then it is going to collapse. It will absorb some energy, dissipate some energy, but it is only a straight line elastic level, and then it is collapsing. So there is no much capacity in the inelastic stage, and the energy dissipation is very less. Whereas in the lower diagram, your capacity gets enhanced due to your after elastic range, you are going into plastic range, and a lot of deformability you are adding to the structure, and you are able to dissipate very higher level of or more quantity of the energy. Sorry. So what happens when earthquake comes? So we have to see the ductile performance and brittle behavior. Now, if we see the shear walls, generally people say that if we have RCC walls in the buildings, we are safe in earthquake. Do we? if the RCC walls are designed properly as shear walls, means designed to take proper earthquake horizontal forces, then it will help a lot during the earthquake. And how it behaves, it is reflected in this image. And if the reinforcement detailing is not done properly, then again in the tension zone it can help. You are able to see some cracks in the tension zone, but in the compression zone there may be chances of buckling of the reinforcement steel, and your capacity of this RCC or the shear wall gets lost, and it may not help you as much as it was intended. So the building can get more damages than it was intended for. So in the behavior, when we want to have ductile shear wall behavior, we have to see that our detailing is adequate enough to prevent any damage of excessive compressive force also. So our steel should behave well in the tension zone as well as in the compression zone to allow adequate resistance to deformation. So you see in diagram A, if the width is BW, the length is LW, and your reinforcement concentration is in the end, which is generally we call it as end zone, or the column type of area where we want to have uh, a kind of end element. This kind of detailing helps in the case of earthquake acting in any of the direction, because earthquake is cyclic loading. Once this time this area is in tension, and this area may be in compression. In the next cycle, this will be in the tension, this will be in the compression. So we have to have a detailing in a manner that we get the adequate resistance at both the sides, because you see in the diagram the strains would be maximum at the ends. So we need more steel at the ends of the shear wall. So one thing more I would like to add, it should be understood by all that when we talk about a shear wall, we generally expect the best performance in the direction of the wall, in plane of the wall. The out of plane direction, the capacity is very less, because we get very less thickness of the wall to help in this direction. So we should have shear walls in the building in both the directions, so that when the earthquake is triggering higher stresses or higher strains in this direction, then this kind of walls would help. And if the earthquake is in other axis, then the shear walls in that direction of the axis should help resist that direction of the earthquake. So it should be have a equal or good distribution of shear walls with respect to both the direction, both the orthogonal directions, to get best performance. So when we talk about in plane capacity of the shear wall, we should see that we have good reinforcement at the ends, and of course if we have added some proper ties as per IS 13920 or detailing, which is confining the reinforcement at the ends, would help a lot, because as you confine with the ties, it is a kind of capacity enhancement in terms of rotation ability. It will prevent the buckling also, because the span of the reinforcement bar would get reduced. The stress on a single bar would get reduced. It will be distributed in a larger area, and of course it is a confined area, so the capacity gets multiplied by many times. As per our basic estimate, you can say that if our reinforcement steel is confined properly, you can get rotation ability, say almost 5 to 7 times. So if we are not giving any ductile detailing, we are detailing it as a normal reinforcement steel column beam system, then suppose your rotation ability of the building is say H by 1000, span by 1000. By giving adequate ductile system, your safe deflection would be like H by 200 or maybe H by 250. So this is the kind of benefit we can get to have economical and safer design just by giving a good confinement reinforcement. And for shear walls, at the ends, we should have a boundary element. We call this as a technical term, it is called a boundary element. At the ends of the shear walls, we add the reinforcement as per the IS 13920. You see here, this kind of element looks like columns at the end of the shear wall. Now, shear wall failure modes due to earthquake. We should also understand if a shear wall is not designed properly or detailed properly, how it is going to fail. Right? It will, when there will be deformation, you can see these symbols above: shear force and axial force is coming on the wall. And when there is a shear force, a cyclic loading, then we get in both the direction, we can have a diagonal failure, diagonal cracking like this. You can see the plan. It is a simple plan, uniformly thickness of the shear wall. Now, if we have enhanced the ends like boundary elements, we have made it stronger. So this area becomes stronger. And now, if we have vertical and horizontal force, if we in the diagram it has been shown only for the x direction. So there will be shear force in this direction. Boundary elements are stronger enough, so there may be some cracks or damages in the thinner part of the shear wall, and that too in this manner. So it will, though because of these columns like structure at the ends of the shear wall, it will help a lot in the collapse prevention, but still the shear wall may have some damages inside. Now, seeing the C picture, now it may have some kind of tension force, vertical compression, and horizontal force. And in that case, due to tension, there may be some concrete cracking at the base. Fixity can also happen. So sometimes what happens, the earthquake forces are more in the vertical direction. And in that way, if the detailing is not very proper, then this kind of cracks, situation C, can also happen. So we should have our reinforcement detailing in a manner that we should be able to prevent such kind of failures. You see the diagram. If the stirrup spacing is larger and shear and the detailing is not proper, you can see that the ties are not properly tied, anchored, and due to a heavier earthquake, the columns are also buckling and the ties are getting broken and the concrete is totally crushed. In the cyclic loading, we can always have this kind of failure. Shear wall failure mode due to high compressive load and flexure. It can also happen, just I have discussed earlier, that some of the bars can buckle in the compression, and in the tension zone there may be some kind of distress in the RCC concrete. And it generally happens when there is a larger gap of the reinforcement, especially near the junctions. So when we talk about the shear wall behavior, the main reinforcement detailing should be like that boundary elements should be provided with adequate confinement, and the central part, which may be considered as less deformation area, because if there will be compression here, tension here, then it will have most of the strain here and here. And similar for the cyclic loading on the other direction, the compression may be here and tension may be here. So boundary elements need to be provided with proper confinement, with having the ductile detailing as per the IS 13920. In the central zone, we may have thickness equal to the boundary element, or we may have thickness lesser to the boundary element as per the stresses, and we can have a nominal reinforcement vertically as well as horizontally. Here the bottom diagram shows that the boundary elements have been strengthened with a larger cross-sectional area, and the central part is a nominal reinforcement with a lesser thickness. And in this diagram also you can see that the vertical reinforcement is also at some distance, and horizontal spacing of this reinforcement bar is also normal. But in the confinement zone, you can see very closely spaced ties to prevent any shear failure in the special zones. Now coming to the areas where we have openings in the shear wall, or we have a requirement of coupling beam, which is a kind of very high shear zone. Now, if it is a normal column to column connection beam, then the stresses are normal. But when we have a coupling beam connecting to the RCC wall, now because RCC wall will be having a very high stiffness, and it is taking almost major part of the earthquake forces. So the beam connecting to the in plane of the shear walls would also have a lot of shear in between. So if we have to have some opening or we have to provide a beam, we should always have this cross diagonal beam system in the coupling system. And IS 13920 gives complete detail how to make a coupling beam. The diagonal beams within the main beam is very important, so as to have adequate shear capacity in the complete beam system. So moving ahead, you can see that this coupling typical beam detail, these diagonal bars are provided through this coupling system. Just suppose you have a lift area, you have shear walls, and you have to provide a door in the lift. So you have to provide an opening in the shear wall. So in that case, just above the door and to the floor level, we have a kind of beams arrangement, and this wall part is to be considered as coupling beam, and in that you have to have this diagonal reinforcement with all horizontal vertical reinforcement also provided as a face reinforcement, because a lot of shear force would have to be dealt by this element. So you can see in the commentary section part also that these diagonal beams are there. In modern times, sometimes to increase the capacity of this coupling beam, in some countries there is a practice of adding steel fibers also, so that we get a lot of ductility, a lot of toughness in this zone, because the shear force will be extremely high. Now coming to the concept of understanding the confinement benefit, you see the confinement effect is there when there is a load, and if there is a kind of axial strain, the force will be exerted on the vertical columns for the axial compression, and with that axial compression again the ties will be taken, considered to be getting out, and if these horizontal ties are placed at a smaller spacing, then the height of the reinforcement bar between the ties will be considered as the free length for calculating the slenderness ratio, and lower will be the slenderness ratio, better will be the performance against buckling. So bars will be prevented from buckling. At the same time, the stress distribution within the system will be better, and the section capacity will increase besides its capacity for the rotation. So this was first diagram is for the circular, but if we have a rectangular section or a square section, then you can see that with the help of this confinement, you can have effective core area which is taking care of the loads is this one, which is shown as a hatched area, and some area will be loosened, so this area will not act as a confinement area, so your capacity will be normal. But as you limit the spacing between the bars and you provide vertical bars closely and then provide adequate cross ties to give a complete confinement action to the reinforcement bars, then again your effective cross-sectional area to take the loads or stresses will be higher. So with ductile detailing, we not only just increase the rotation ability, it increases the overall load carrying capacities also. So you can see in this diagram, the above diagram, if we are seeing the hysteresis loop, as I discussed earlier, that if a uniform hysteresis loop is there, it is going to dissipate the energy uniformly and would perform better. In this first diagram, you see there is only one outer main ring and there is no internal ties of the vertical column. And if we have a cyclic loading on this square column, then you see this very randomly distributed diagram in which we have initial few cycles which are fine, but as the cycles are more, your stress taking ability goes down and your performance of the column goes down. Whereas in the lower diagram, if you see, because here we have provided the ductility requirements and all the vertical columns have been tied, you see the hysteresis loop. It is a very uniform hysteresis as the formation is increasing, but behavior is not changing and is able to dissipate energy in a uniform manner and the performance is perfect. So by providing these additional ties, we have improved the overall performance of the detailing or the column of the performance or load ability of the column to a very great extent. So this is the property of confined concrete. You see, if a normal column is there, then it is going to behave like this. Its rotation ability, say epsilon CO, maybe after 2 epsilon CO, it will be having a very low potential of taking further loads as it is already going and the curve is already going very down. But if it is properly confined, then you see the curve is going up, up, up. It is taking more load, compressive stress taking capacity is more, and then if you see the strain ability, it is taking more and more rotation. And then again in confined concrete, you see the capacity is again high to take the deformations and very high epsilon Cu level you are able to reach when your structural element is confined in the special zone. So you see the unconfined area, your strain is say 0.002, maybe 0.0025, and ultimate consider is 0.005. In our designs, generally we consider 0.0035. So, but if we have a confinement, then you can see that typical values for ultimate compression strain Cu may be having 0.012 or maybe 0.05 also. So you can see the value for a non-confined area, it is 0.005, whereas for the confined, it is 0.05, almost 10 times. So by increasing the ductility, by improving the system of confinement, we actually increase the capacity to almost 10 times. And which capacity? Capacity of deformability. So that is why we use the term as ductile detailing. So in the design, if you are taking this kind of behavior, then practically also it should reach to the execution also. So in the execution, sometimes what happens, the easy areas are taken care with the ductile detailing, but certain areas at beam column junctions, engineers do not supervise properly, and those areas are open to unconfined areas. So we generally lose the capacities which we were intending in the design, and we actually do not get in the situation of the earthquake. Similarly, when we have a system of detailing, our sizes of column should be adequate enough that we get the development length within the beam depth zone. Now you see, I am specifically taken this slide to tell you that IS 1893, sorry, IS 13920 to 1993 version was showing that you can take this top bar quite below also and bottom bar up to a higher level also to provide the development length. But in the 2016 version of the code, it has been improved to a level where it shows that all the your development length should be within this confinement zone, because when there is a stress, your this area is acting, and if your reinforcement is above this area will also already have a hinge formation, or maybe here there will be hinge formation, so above area will not help much. So column sizes should be chosen adequately to provide development length within this depth. You see it through these diagrams that this, if we see diagram 1, if the bar is going like this up or bar is going down, bottom bar is going down, it is not helping in this zone. So your concrete is getting crushed within the crack, within this beam column junction. Another pictorial view that beam bars bent inside but not adequately given the horizontal ties. So again, the shear force inside the beam column junction is troubling the system and making the damages inside the junction. So we should have proper reinforcement within the junction also, and then we can see some hinges being formed in this area. So in our design, generally we have a concept of strong column, weak beam system. If we are able to make that system, then there will not be any hinge in this column. If we have provided proper reinforcement within the junction also, so this column area will be protected in the junction also, and there will not be shear cracks. Whatever hinge will be formed, the hinges will be formed in the beams only, which is easily repairable. So after the earthquake also, there won't be much damage to the structure, and whatever damage we could find through the hinge formation, we can easily repair that. Now, how to actually provide that? So you see, you can always have joint hoops. It can be provided like a stirrup, or sometimes if the stirrups cannot be provided within the junction, you can provide some C-shape reinforcement also, some C-shape types also, but best is that you provide proper ties within the beam column junctions. Right? In this diagram, you would be able to see that in the beam column junction also, we have proper rings and cross rings, small rings, so that we are able to tie all the column reinforcement. And in the elevation also, you see proper reinforcement is within the beam column junction. It is very important because we don't want that the shear force, which is having a very high concentration in the beam column junction, should not be able to damage the column inside. So this is again showing similar example of exterior. Earlier was the interior. It is an exterior column, corner column, and it is also to be confined properly. So I would like to have the second poll.
Would you like to launch the second poll?
Yeah, please second poll.
We would request all participants to please put in their votes.
So what is the poll result? Can you please read the question and the poll result?
Yes, sir. So 53% are voted for adequate concrete cover, 9% for larger diameter of rebar, and 38% for strength of concrete.
So again, you see that here the opinion is divided. Would you please again repeat the option, the poll result? Option
Sure,
A.
sure. Option A, adequate concrete cover is 53%.
Okay.
Option B, larger diameter of rebar is 9%. And option C, strength of concrete is 38%.
Right. Very good. So many of you are very clear about the requirement of the cover. So I would be discussing that here again. Now you see this slide, and in this slide you would see generally this is the practical problem of the project site, that the reinforcement steel which has to cross the column, the beam reinforcement which has to cross the column, how to take it. Sometimes the site people do it like the reinforcement of beam taken outside the column, because the cover of the column, cover concrete of the column is generally 40 mm to the reinforcement, outer reinforcement steel, if the environment conditions are normal. In extreme cases, it may be maybe 50 mm to the stirrups. But for beams, generally it is 30 or 35 mm. Now, if the reinforcement bar is coming almost 35 mm from the beam face, and if the column side and beam size is same, then the beam reinforcement is going to hit the column reinforcement at the end and towards the outer side. But to get better confinement behavior of the junction, we want that the beam reinforcement should go inside the column. So what would happen? Either some people may disturb the column cover and take the column reinforcement outside and the beam reinforcement slightly inside. Now that again pose some problem. And if we are taking the beam reinforcement outside, then the cover to the beam reinforcement goes very, very less at the junction. So all these conditions make the system vulnerable to the deterioration at a faster pace. Now, what should be the solution? Now, solution should be, first of all, if we can have larger column size and lesser beam size, then the reinforcement bars can be simply taken inside without any problem. And structural designers can plan the system in a manner that the beam reinforcement and the column reinforcement do not interfere with each other. But sometimes it may not be possible, or if even if it is possible, sometimes the one face of the beam is to be having flushed with the column face. Then what should be done? So this diagram clearly shows that you have to take the reinforcement of main reinforcement of the beam inside the column reinforcement. And now what will happen if you are taking the beam reinforcement inside the column? Then what would happen at the beam column junction? The cover to the beam bar would be higher. You see this ring is loose and the beam bar has gone inside, and the cover to the main reinforcement here would be very, very large, maybe 70, 80 mm it will become. Now, if the cover is too large, it will tend to crack, and capacity may also get reduced a bit. So what is the solution? So solution is here in this diagram itself, that you take the main reinforcement bar which are taking the bending moments inside the column so that you get proper confinement behavior, and you can simply add 10 mm or 12 mm rod just on the face of the column, just like your column stirrups. This bar can also travel within the space of that stirrup, so that cover is not changed. Your beam reinforcement cover is also unchanged, so beam will not crack in this area because of the higher cover. And by these additional face bars which are taken at the face of the column can help durability of the structure, as at the same time beam main reinforcement helps to get the complete moment capacities, right? So detailing of the construction should be like that. There should not be too many layers, and there should not be too much of congestion at the beam column junction. Sometimes it happens that there is an inverted beam and so much of reinforcement, and then the junction becomes a bit not very effective. So the designer should try to avoid a situation where we have multiple layers of reinforcement steel and too much of congestion. Adequate size of column and beam should be taken to have adequate reinforcement of compression and tension, and wherever required, we can have face reinforcement.
So, one question that we have is from Mr. Harvinder Singh, who is saying that can we allow buildings to deform so much under lateral load, and what should be the permitted displacement?
Now, very good question. First, the first question is very pertinent. Though in the discussion, I was trying to tell that we have a lot of deformability. Now, deformability means we have a system where we can have, if excessive earthquake is there for a very, very short period, then there should not be any damage. The code says that our deformation limit should be such that it is H by 250, or 4% is the allowable deformation in the building. We should not allow more than that for any interstory or the overall drift of the building. So
All right.
overall drift will be only up to 4%. Yeah.
Thank you. In fact, we also had one of the registered listeners asking us a question before the session, and they said that what is the torsion effect in corner columns?
Pardon, what is the
Torsion effect in corner column regarding
tolerance
with respect to ductile detailing.
in corner column? What is the
Torsion effect, TORSON.
torsion effect? Okay.
Yes.
Well, generally, torsion of the building itself will have a bigger role to play. It is not only that the torsion will have in the external column or external column beam junction. There might be some mild effects of the load or the geometry which may have some torsion effect, and that torsion will be converted into shear, and that shear will be taken care by the stirrups. But torsion itself is a very big important question, because when we design for the earthquake safety, our placement of columns, the column sizes, the shear walls, all should be such that in general there should not be rotation of the building due to torsion. Our building should have, suppose your earthquake is in X direction, then there should be lateral displacement in the X direction. If we apply earthquake in Z direction, then your lateral movement should be translational in the XZ direction. So first two boards should be straight only. Only in the third board you can have some kind of rotation. So torsion should be minimum in the structure. Lesser will be the torsion, best will be the performance during earthquake, and the design will be very economical. So structural designers should have a very important role in planning the column sizes, placing of the columns, the placing of the shear wall thicknesses and all, because we don't want torsion in the building as a whole.
Thank you. So there is one question from Bangaru Swami Kamraj. If you can actually, I will read it out, but it's quite a technical question, so maybe you can open it on your screen also. He is asking what is the XU max for high strength bars like FY 550 and FY 600?
FY 500, FY 600. Now, when we talk about very high grade reinforcement steel, the parameters of the steel requirement are given in IS 1786 reinforcement steel code. But at the same time, very good question that when we talk about the strength of the concrete to be compatible with the reinforcement. Now, in my first question, I had asked about the strength of reinforcement bar versus ductility. Now, strength of the reinforcement bar would help in saving the cost to a larger extent. But at the same time, we should select a proper grade of concrete also. Now, all of you might be understanding that, we might be knowing that IS 456 is also under revision. And in the upcoming standard of IS 456, there will be a table which will be guiding you that when you are using the higher grade of steel, say Fe 500 or Fe 600 or Fe 550, the compatible grade of steel. Now, I would like to explain you in a manner that if we are having very high stress capacity in the bar, say maybe Fe 600 if we initially talk about, the modulus of elasticity of the bar is same as it was for IS 415 or it was for IS 250. So it means that higher is the grade of steel, it will allow more stresses, safe stresses, but at the same time the strains will be more. So at one time the stress is higher, so the interface zone, the area which is in touch with the concrete should be good enough to take that stress, because now the stress transfer to the composite system would be that transition zone between the reinforcement from the face of the reinforcement to the concrete anchorage zone. So the concrete anchorage should be good enough. So we will be needing higher grades of the concrete. So probably when we were using Fe250 grade, M15 grade or M20 grade was good enough. Now, as we moved on to Fe415, the minimum grade of concrete in IS 456-2000 was improved to M20 or maybe M25 in the some environmental condition. So it was good enough to use M25 for Fe415. But now, as we are moving Fe500, Fe550, or Fe600, we need to use the compatible concrete grade also. And for that, generally, we consider that for Fe500, M30 grade is good enough. But as you go for M550 grade, M35 grade is compatible. And if you want to use if you want to use Fe600 grade, then to get best advantage of that reinforcement steel, we should use M40 grade concrete for the best benefit in terms of saving of the cross-sectional area of the system, or maybe having the best economy by saving the reinforcement steel also. Because as we are increasing the strength, our requirement of steel cross-sectional area will reduce. So overall consumption may go down. You can get financial advantage of saving the reinforcement steel. But at the same time, if you are using higher grade of concrete, it will again help you reducing the reinforcement steel, but with a better performance. So I would suggest that when we choose very high grade of reinforcement steel, we should select appropriate, a bit higher concrete grade, so that any larger strains are taken care, larger stresses in the interface zones are taken care without any internal cracks or damages.
All right. So we are almost out of time, so I will just take one last question from Mr. Dinesh Balu. He has
Yeah.
asked regarding stirrups. 150-degree bend for both is required, or is he asking that is it 135 degrees for one and 90 degrees for the other? So is it 135 for both?
Well, very good question. Generally, what we want is that for the outermost stirrup, the master ring should have 135-degree bend for all these stirrups. But for the internal ties, which are tying the internal columns, internal reinforcement bars of the columns, one side should be 135-degree bend, of course, because we want the anchorage at least from one side, and other side advantageously it is 135. But if it is 180 degree, or if it is 90-degree bend also, it is also adequate, but it should be staggered. Like in one direction it is 135 one side and 90-degree other side. In the next row it should be 135 from the other side and 90-degree from the other side, so that we get proper distribution of the anchorages. This 90 degrees are allowed just to have a system that which is practically more feasible to work it faster, because one side you take it 90-degree bend and other side you can quickly make 135-degree. So both are good. 135-degree is the best, but 90-degree on one side is also acceptable, but it should be staggered.
All right. Mr. Dinesh actually has a follow-up question regarding stirrups itself. He is asking, should it be 415 Newton per mm square, or should it be 550 Newton per mm square,
Okay,
which is preferable?
now it is again a very important question. I must appreciate all of you who are attending this session. As per the codal provisions, what we consider as the strength for the stirrup is that the as concrete, the strength of the steel we are considering to be 415 only. We are not, though you can use the steel of 500 grade or 600 grade, there is no bar of using higher grade. But in the design calculations, the strength considered would be only 415. I tell you why. I'll take a few seconds for that. In our presentation, we discussed about the confinement effect. And confinement effect means we want that the concrete should not crack under the strains. Now, if we want the concrete to be within a allowable strain, the confinement should give higher resistance to deformation. The reinforcement steel would have more deformation at higher stresses. So if we allow to design with 600 MPa stress, it means we are allowing the strain equivalent for the 600 MPa stress. So we cannot allow that kind of stress in the reinforcement steel, because it will deform more under that level of stress, and the concrete can crush before that. So in the shear zone, we have to be very serious, and we have to be very sure about the safety of the concrete, and that can be ensured by giving more and more confinement. And that is why our code says that even if you use higher grade of steel in the design calculation, please consider only 415 MPa for the stirrup design. I hope I am able to answer the questions of the
Yes, sir.
audience.
Actually, as you're talking, a couple of other questions are also coming. So I will just take maybe 5 minutes more and we will try to answer one or two more questions.
Okay.
Mr. Deepak ji has asked, and this is further on the topic of stirrups itself, that in calculating length of stirrups, whether we need to add the bending length or neglect the bending length, which is correct.
When you are calculating the length for the bar bending schedule, you have to calculate the actual length, because the bending length is also be there part of the length of the steel. Now there are methods of calculating where for the bend you reduce certain diameter, because if you are considering from the outer direction, outer face, then because of the bending the length increases. So it is a matter of calculating geometrically. So there is no other technical aspect behind that. Whatever the actual length is required for the bending, and maybe for the 75 length hook, you have to calculate for that.
All right. And we'll just take one last question from Rama R. And he's asking that which portion of the beam or column is chosen for lapping of longitudinal rebars?
Okay, again a very pertinent question. When we have to ensure that the beam column junctions should not crack or should not have any damage during any lateral movement or the earthquake cyclic loading, the junction should be the areas where we should prevent any kind of lapping. So for the columns, the beam column junctions, and specifically H by 5 from the junction areas are prohibited for the lapping. And in beams, because the top reinforcement acts as a tension reinforcement in the beam column junction, so top reinforcement should also be not overlapped, or the lap splicing should not be provided in the top reinforcement. For bottom reinforcement also, if we can prevent the junction, it is good, because we do not want congestion of reinforcement at the junction. So in bottom reinforcement, we can have some kind of overlapping a L by 3 zone, but for the top reinforcement, it is preferable to have lapping in this middle part of the beam. So in the top reinforcement for beam, in the mid section, for the bottom reinforcement of the beam, anywhere between in the central two-third area of the beam, and for the column reinforcement, there should not be any junction, there should not be overlapping in the junction, and certain height, maybe 600 700 mm above the junction and below the junction. So this is the minimum requirements. But I would like to add one more point here, that coupling system is better than the overlapping for the development length. For specifically for the reinforcement diameter of 20 mm or more, the IS code IS 13920/2016 allows to use couplers in the no splice zone also. Like couplers can be used near the junction areas also, because when you use coupler, the congestion is not increasing. Your concrete will be placed properly, and you are going to get adequate or full strength of the reinforcement through the coupler. So there is no weak zone made. So if we have to provide splicing near the beam column junction, then please use couplers. Otherwise, try to make your bar bending schedule in a way that the splicing is avoided near the beam column junctions. Right?
Thank you so much, sir. And once again, thank you for not only giving us a very informative session, but being so generous with your responses to all the questions. And with that, we would like to end the session. Thank you so much to all the participants. We would, of course, urge you all to please, attend the next all the Tiscon webinar sessions that we have planned, the discovery sessions. and you will be receiving a small survey from us. So if you can please give your feedback via that, it would be good. Thank you so much. Bye bye.
Thank you everybody for patient listening. Thank and best wishes to all again on the occasion of this Engineers Day. Best wishes to all of you. Thank you again.